Okay, welcome to our talk. The main part is a repetition of what we did at Congress, but we have some additions and some more technical details. And the important part is we have a workshop afterwards. So if you want to bring your own Fitbit, or if you want to hack one of those that we brought, this is going to be a session that is much more interactive than at Congress. So, the motivation. After publishing our first paper, we had some stuff in the press where they said, well, you can hack Fitbits. And so the fun part was, dear hackers, please update my Fitbit so that I can run 10K every day, and you can see my weight either way. So people want to have those stats and they don't want to do any sports. And I mean, it's quite good to have those stats. I mean, you can even get some points at your health insurance and so on, even in Germany right now. So better have some good stats somewhere. And the question is how to produce them. So if you look at the system of Fitbit, they have end-to-end encryption. So every tracker has a key that is rolled out in factory, and you cannot really access it except from opening the hardware. And the same key is on the server. So it looks quite nice. Then you have on top the limitations, so the tracker itself, it just has Bluetooth. So it cannot directly talk to the server, but you have an app that is relaying the traffic, but not modifying. So even though the Bluetooth connection is not really secure, it doesn't really matter. It's just end-to-end encrypted. And they did a lot of things right. So this end-to-end encryption, it's so in the old trackers it's some XT encryption, but the new trackers they have AES encryption, and they use an IV and everything. So they do things properly. If you use the hardware, the standard configuration is that during boot the debug interfaces are disabled, so you cannot see anything in the debugger. And it's almost impossible to brick your tracker during the update process because it's separated in BSL and app part, and you boot into one or the other. So it seems to be a very solid system, even though we found some things, of course. And during responsible disclosure, they have a complete security team that is really responding fast. They gave us back a list of the things that they understood and said like how severe is it and so on. So they really have a good process for this. But yeah, we found something. So far it might not be that good. So when we started, we didn't have any clue what is happening. So, I mean, you can see some stuff in Bluetooth, but it's still a bit strange. So we started dissecting the smartphone app. The smartphone app itself is quite nice because if you can modify it, then you can easily see how the protocol works and confirm your protocol assumptions. So you just say there's some authentication and I want to exchange something in there, and you don't need to understand the complete OAuth flow or web API or something. And you can start this by enabling some debug flag. Then you will also have a nice output in your ADB logcat. So you will just see every step, every function that is called, all debug messages, and see what is happening in there. And from that you get the class names, and then you can modify all the things that you want. And I don't know if it still works for the most recent app, but yeah, like some weeks ago it was still working for the app that was back then out there. So you can just modify it and confirm everything or modify everything. And then we found out if you have this debug or developer options, then some more options appear in the menu under the help whatever thing. And you can configure additional settings. And those settings are quite nice. So some of them were pretty useful when we did our dissecting of the protocol. For example, you can enable a proxy server. Which we just used for man in the middle, because that's much easier. Then you don't see the traffic of all the other things happening on your smartphone, just the Fitbit app. And then we found out you don't even need to recompile the app for this, because there is some configuration settings in the files, and so you can just run even an unmodified app and change those settings. Yeah, so so far it still seems kind of good. I mean, you can just modify and sniff things, but there's encryption. So to actually break something, you need to check the encryption flaws, or if encryption is working properly. So if you look into the program flow, you have a very special pairing process. So it's not using some standard Bluetooth pairing, but you just connect to a tracker, and then you do a special pairing that seems to be a standard Bluetooth pairing. So you see on your displays normally some code that is displayed and that you need to copy. So that's the third step. So after just connecting, you have this copying of the pin on your tracker and so on. And this is sent to the server, and the server verifies the pin actually. So it's an end-to-end authentication and association with the tracker. And by this you prove that you own the tracker physically. So you can only know the pin if you have the tracker itself and see the pin on the display. And then the server has some special stuff. So the server can give you back something that is called authentication credentials. And those authentication credentials are stored in the app, and the app can then do some special actions, which are authenticated commands. So the special actions you will see later because we need to use them for some funny stuff. The thing is that this is not really secure. So there's those old Fitbit flags that don't have a display, and they don't have a pin that they display, so you can just pretend that you tapped the display by sending a local command, for example. And even on the newer trackers, so if they operate in plain text and you didn't update them properly, you can exchange, of course, the pin or replay stuff. And so it's somewhat secure. So on the newest trackers, it is, so to say, secure because there's the encryption and so on. But on older trackers, don't trust this too much. Now the fun part is if you have authentic credentials, you just get them once from the app or from overhearing some other pairing or something like this. They stay valid forever because they are bound to the encryption key that is stored on the tracker. So you cannot exchange something there. So forever valid authentication credentials is the big flaw here. And then you can have fun. So the fun part, the first part is you have some authenticated memory readout in the app. You just send a command after authentication. You say, please give me all memory contents from here until there. If the range is somewhat invalid, like too long or something, then it stops putting out data at a certain point. But until then, it just replies everything that is there. And you can read out all memory parts, so you can read out the EEPROM or the flash that is then you're going to explain later. And with this, so the fun part is you can even read out this encryption key. So authentication key means on those trackers that are vulnerable to this that you also have the encryption key later. And then you can do things without the server at all. So just do everything the server does because you can do encryption. And then there is something that even works on the newest Ionic smartwatch with the authentication credentials, because you can do something that is called live mode. So normally, if you have data on the tracker, you have the problem that you need to transfer a dump to the server is decrypting everything and so on. So if you have something like heart rate data, it would really take long to see the heart rate live. And it would also cause a very high load on the server. So what they do instead is this live mode that is plain text and just has authentication before, and then so you close the standard session, open a new session, and then you see this live data. So this contains a timestamp, the distance traveled, the step, calories, and also the heart rate. The timestamp is a Unix timestamp in seconds, so it's just the data in this specific second. You don't get statistics that were collected by the smartwatch or a tracker or something. You just get the average data or the data of this specific timestamp. But you can get things without the server. That's at least something. So if you don't want to use the server at all and establish a Bluetooth connection and run live mode all the time, you could use your smartwatch without a server. Okay, now this is all a bit limited, so we started with the hardware access, which is now Daniel's part.
Yep. So what Jessica told us up until now was mainly the part about the app and what the app talks about with the server, so and the Bluetooth connection, of course. But to have a complete picture of how the system works, we also need to look into the firmware of the tracker itself. So this is broad overview what is inside the Fitbit Flex. So we have the main system on a chip. So it's an ST microcontroller here, and it's an Cortex M3. And of course, there's also the Bluetooth chip and the accelerometer. So and apart from this, so we also know a few libraries they used in the firmware. We don't know the operating system they used, but for example, we know that they use libtomcrypt for the encryption stuff, and we also know that they use some kind of library which is very similar to this libble shield library, which are just and both of them are just freely available on the internet. And with this knowledge, you can really improve your reverse engineering, or at least it gets easier. So the next step is that we took apart the Fitbit, and so this is what comes out. Ours looked a bit better, so here the guys from iFixit broke some antenna stuff over here, but it's a very nice picture. And for us, the most interesting thing was the SWD protocol. So with SWD, you have full access to the microcontroller and also the complete memory. So if we want to know what's inside the firmware, we want to get SWD access. And for SWD, we need essentially 3 ports. So TP8, 9, and 10 mainly. TP10 is for resetting the Fitbit, but this is not really necessary, but really handy to have. And for ground, we can just use the ground pin from the battery. And also, if you want to power the whole thing, you can just use the default connectors for the Fitbit. So with this, we are able to dump the complete firmware, and we are also able to see what data is actually stored inside your firmware or inside your Fitbit Flex. Also important to note, we will talk here about the Fitbit 1. So this hardware is about the Fitbit 1. So in case you download the firmware from the tracker, so this is our setup, so it looks kind of crude, but it worked for us. And I also have it on the workshop place, so if you want to see it, I think it still works. And yeah, right, the firmware consists of mainly 3 parts. So a flash, an EEPROM, and an SRAM. The flash contains the firmware code, of course, and the EEPROM is used to store values which should survive on an empty battery. And the SRAM is used for the firmware variables. If we have a closer look into the firmware, we will see that the flash contains of 2 main parts, which Jiska mentioned earlier. And so this BSL part consists of about 500 functions, and the app part of about 1,000 functions. And they use these 2 partitions, so yeah, you can call them partitions, to always have something which is still capable of booting in case something goes wrong during flashing. And of course, both can run independently from each other. So this was the flash. Regarding the EEPROM, this contains everything which is necessary for encryption. So your serial number, the encryption key, the symmetric key, which we saw earlier, and also an encryption switch, which you can just use to completely disable encryption. But then the Fitbit will not talk with the server anymore. This is another story. And also your fitness data, of course. So what we also wanted to do, so Jiska told you that the debug access is disabled by default. This is right, but the thing is, right after resetting the Fitbit, you can access via the debugger the Fitbit and download, for example, the whole flash. This is no problem. But if you want to have, for example, GDB access, so to have the possibility to also add breakpoints or memory watchdogs, you can. This is not possible. So what happens is that you start your debugger, you connect it to the Fitbit after reset, and then you hit continue, and the software runs. And after a certain point in time during execution, the GPIO ports got reconfigured to something else. So this means that your connection to your debugger gets disconnected. And so we thought about what can we do about that. And from a previous project, we also have this Nextmon framework. And this allows you to binary patch arbitrary code, basically. So especially is this good for ARM code. And what we did is to so with the flash with the debugger, we can read and write arbitrary flash, but we can not do live debugging. So what we did is to read the whole firmware, patch it, and write it back. So just to enable these GPIO ports. I do not really know where they got disabled. I do not care, but I know up until a certain point in execution, okay, so now they are disabled, and then I just build a small patch which re-enables them. So when I connect then with my patched firmware, my debugger, it connects, and then after reset, then I hit continue. The firmware runs. I get quickly disconnected when the software hits the point in time where it reconfigures the GPIO ports, and then my patch comes again and reconfigure it again to be able to debug. And so this works fine. And with this, we are able to have dynamic debugging, which is really handy if you want to do further reverse engineering. I can also show you this setup for in our workshop if you want. So, okay. And now Jiska will tell you more about wireless hacking, firmware hacking.
Yeah, so the fun part is if you have the firmware, then you can also obtain the firmware update process. So I had just some assembler code, of course, but at least something to know how the firmware is flashed, and then flash my own firmware wirelessly without opening a tracker. Because it's much easier if you have like a closed tracker that does something special in addition, and then but everything else just behaves normal if you want to fake data, for example. So if you look into the update process, in every dump there is a firmware version, so the server knows always which firmware version you are running on your Fitbit. And if there is an update, it just tells the user via the app that there is a new update. But the update process itself is always triggered by the user, so you cannot, normally you should not be able to just trigger an update because the tracker needs to be charged and so on, so that this is ensured, you just update it yourself. So you just tell the tracker, well, I want you to update, and the app also requests a firmware update from the server then, and it just gets a binary, and this binary is then flashed. The binary contains first the BSL part. The BSL part on the tracker itself is first validated by some steps, and afterwards only flashed. So if you don't pass a certain amount of checks, it's not even going to be flashed. And in the end, you reboot into the BSL, and then from the BSL, you flash the app, which has the same steps. And in the end, you should just reboot into the app, so you don't do this actively, but the tracker does. And everything should work then. So this is this fail-safe part. If you break the BSL, you cannot reboot into the BSL, but your app is still valid. So this is very stable compared to other possibilities that you normally have. But so we could do a lot of experiments without pricking the trackers. That was very nice. Okay, so the update format. It's a bit complicated. First, you have the tracker ID. But only the first byte, which means you cannot flash like something like a Fitbit 1 firmware onto a Fitbit Flex or something. At least not if it's not on purpose. And then you select if it's the BSL or the app, or if you want to reboot into app or BSL. And if it's BSL or app part, then you also have the memory address, the length, which is there twice, I don't know, a CRC, and then the actual data. The data has an upper bound in size, so you will normally just add multiple of them. So if you have the app firmware, then you have 3 data chunks, so 3 of these, it's flex, it's app, it's memory address, blah, blah, blah. And then you have one empty chunk to say it's finished, and then one reboot chunk, which is then rebooting this thing into the app. And this complete thing again has then a header and a trailer. The header tells you if it's encrypted or not, has again a length field for whatever reason of the firmware, but also the frame has a length field here. And the trailer itself either has again a CRC, I mean there's lots of CRCs in between here for the chunks, but it also has a CRC again. Or if it is encrypted, then you have this XT encryption with MAC authentication code. So the firmware checks, so if you would just draft the firmware from this, it would still not run. So you get nice error messages, but it will not be flashed. So the additional checks are the address range must stay within BSL if it's a BSL update, or within app if it's an app update. So far, so good. And then within the firmware, they do somewhere flip a bit to 0, and then they have a CRC that is not CRC'd itself, but the rest of the firmware, and then written somewhere. And if something fails in this process, then all the dumps that you will get in the future from the tracker will have the version 0.0 in the dumps. So you will just see, okay, the app or the BSL update failed, and it has the version 0, even though things in between were okayish, but not okay enough. Yeah, so if you modify the firmware so that it passes those checks, you can just update the tracker. But you also need to understand encryption, so that's another part. If encryption is enabled on the tracker update must be encrypted. And there has been some code by Martin Schelbes, but the code didn't contain the CMAC, and if you don't have the CMAC in there, you will get the error message that there's a missing trailer signature or something. So we have its 2-byte nonce in each header. We use the encryption key, and then importantly, in the end, we need to add this 8-byte authentication MAC. That's everything of this is in this EAX mode. You can just use the libtomcrypt and you will have it. And the encryption library that is used by the app, this Spongy Castle or Bouncy Castle libraries, they also have all those functions. So you don't need to think a lot. You can just use the libraries that they already use and use some other calls. Yeah. So that's it. Then you have the encrypted firmware that you can flash. And since this is all a bit complicated, I mean, I had some Python scripts running this, and it worked for me and for my encryption key and for my tracker, but we decided to publish a complete framework that is capable of doing all those things.
Yep. So now we have basically everything to patch our own firmware. So we can download the complete firmware. We understand how it is composed. So what we need to do to create a firmware update, and we also know where the key is and how we can get it from the tracker. So what we build is the following. On the right-hand side is your tracker. Then this is a smartphone app which we wrote by ourselves, and a PC which runs our modified Next1 framework. So in the first step, you would get the key from your tracker, then get the plaintext firmware, transfer the firmware to your PC, modify it with the Next1 framework, and then basically transfer it back to our app. And then again, you can use the app to create a valid firmware update and also encrypt it. And then you can also use the app to flash the modified firmware back onto tracker. And for both the app and our modified Next1 framework, everything is online on these two links. These two links should also be available on the description of this talk. And that's it. You can arbitrarily modify the Fitbit firmware, and this can look like this. So this is a default Fitbit Flex, and this is the original Fitbit app. And this is basically the firmware part which is not fixed yet. So this is again, I think at beginning of October or something like that, they released a firmware update which fixes the problems which we told Fitbit, right?
Yeah. So that's the version 88, so 7.88, and I just downloaded it. I had the encryption key because I mean it had an old firmware before, so I just modified the 788 with the step counts by 100, and it has some funny side effects. So you can there's a reset pin for the tracker so that it's resetting even if it's in the original casing. And if you reset the tracker, then for some reasons the steps by 100 is applied 2 times, and then you have something like the total steps count by 1000, and you can do this multiple times, and then some counter is also running over at some point. But so after synchronizing my tracker the first time with the server, I just got some funny emails like, you have the New Zealand badge, you just walked the whole distance of New Zealand, and all this kind of things. It was pretty funny because I really had like 5 emails like this special badges or something in my inbox, like, oh, you ran 100K in one day and everything just at once. Yeah, so if you have this patch and if you just reset the tracker, so it has in the charger it has a small hole where it just can that you can press. And then you have this reset and these super high steps. Don't do it too often because if it's more than 2 by 31, it just resets to 0 again, and then you need to count up again. Yeah.
So there's integer overflow.
Yeah, there's integer overflow.
Okay, so I guess we have fulfilled the wish of this comment in the very first slide. So, yeah. So there's more to come. Do you want to talk about it?
Yeah. So. We know roughly where the accelerometer data is stored in the memory, so we can just put this out in live mode, which is pretty nice because you can just see the raw readings then. The limitation is that it's just Bluetooth, and the accelerometer runs faster, so you just get a value every now and then, and it's not as fast as the tracker, of course. But you could also process the data locally, and then you could do things that the tracker does not do yet. And another fun part is, so for this modification, it only increases the steps. So you might notice that except from live mode, so if it goes back from live mode to the normal mode and then back again into live mode, it has this super high step count, but the distance in miles is still accurate. So you ran like 100 meters or something with 10,000 steps. So this is still something we should need to do. And then also at Congress there was a nice hacker that contacted us. He's called Hugo, and he wrote some Python stuff around the Unicorn Radar 2 framework, and we can now also simulate the firmware or emulate the firmware and do some funny things. So currently we started fuzzing frames into the Bluetooth stack and other things like this. If you have some feature requests, please tell us so that we know what to do or what to modify. Not just the 10K a day, but I mean we can do everything. Yeah, and so there's some limitations. So the problem is that you can only read out the encryption key on old trackers, so don't update your firmware. But if you buy a new one, I just bought some weeks ago a brand new tracker, it still had an old firmware version and so on. So no problem for me. So if you just buy something new, they didn't patch the ones that are in stock in whatever store. And the live mode, I mean, it's still available for the Fitbit Ionic. I don't know. They tell you that you can disable it somewhere. I don't use the original app that often, so maybe you can. I don't know. They told us so. In summary, yeah, go out and you can even flash your neighbor's devices if they are still on plain text. No user interaction required, actually. You can keep control of your own data. So if you interpret the dumps and so on and have the encryption key, you don't need to transfer it to Fitbit anymore. That's something where parts in the app are still missing to actually interpret the dumps. So we roughly know how they work, but we don't do it yet. And you can also run any other code on your Fitbit, like if you want to do, I don't know, draw motions in the air and then do something in the app, for example, you could do this. if you want to program that. But okay. And yeah, then Daniel just had the idea, let's order some more trackers for the workshop.
Yeah, so this was the initial idea. So we just ordered 2 of these packs, so 44 of these broken fitness trackers. And the idea was to just throw them into the people, but yeah, unfortunately they did not arrive in time. So, which also means we now have 44 broken trackers in the next few days arriving.
Yeah, mine will arrive on Monday, it says.
Okay.
Yeah.
Cool. 2 days.
Yeah.
Late. Yeah, but there is always a next CCC event, I guess. So.
Yeah, and also, so typically those broken trackers, I mean, we ordered some of them before, so we have some trackers in our workshop, don't worry. The battery is typically a bit broken, but if you tear them down, that's not a problem. So it's still a very nice source for research, debugging, whatever, or you just solder in a new battery and reassemble. It's also possible. Okay. Any questions about what we presented? Any feature requests? Something that you want to do with your tracker that was not possible yet? Yeah?
Is somebody working on an app that would enable you to use your tracker completely without an online account or something like that?
Oh, sorry, there's just a microphone arriving.
Please repeat your questions for the
for
recording.
the video. My question was, if somebody is working on an app replacement or feature for your app, so you can use the tracker as a normal tracker without any interaction with the server or having even an account.
Yeah, so for this authenticated commands, you need an account once. So that's what our current app does. You log in and you then get the authentication credentials, and then it's working without the server anymore. Currently, this is just live mode, not the normal dumps. For the normal dumps, I try to get some students working on this. So, I mean, the new semester starts in 2 weeks, and hopefully I will get students on this because I'm a bit limited in time, but I would know how it works. So I can tell you this is the format and this is roughly what you need to do. So if anybody wants to work on this and I don't find students, you can also do this.
But there's currently no one working on this.
Yeah, but in 2 weeks probably. So, I mean, I plan to do this.
Okay. And the key you get from the server is what you also need for the encryption?
No, it's an authentication key, but with this authentication key, you can get on all trackers the encryption key.
Okay, but they patched out the read memory command, so
Yes.
you can't do it on the newer firmwares.
Yeah, but if you buy a new one that was not talking to the server yet, it works. Because the firmware update, they are still shipped with this with the 64 or 81 firmware and not with the 88. So the Fitbit Flex.
So how does the app get the key for the newer?
Not at all. We don't. So I mean, maybe we will find some buffer overflow or something, but we didn't find.
No, but how does
something.
the app work then?
What?
So how the update process works, or what?
Or does it work from the server? If the app doesn't get the key anymore, or where does it get the encryption key at all?
The key has never been on the official smartphone app.
It's always between the server and the
Yeah. So this is not a standard feature. Yeah.
Okay, thanks.
Okay.
No more questions. Who wants to join the workshop? Yeah, that's great.
Cool.
That's great. Yeah, because we have some to tear down. If you want to tear down one and look into it, you can just do this. Great. Okay, it's in the room C-ball. That's if you walk this floor down and then cross the hack center and then walk up again.
No, straight. Okay. Cool. Thanks.